All right, number 41. For a given large sample size, which of the following gives the smallest margin of error in calculating a confidence interval? All right. So we want the smallest margin of error. As the confidence level goes up, the margin of error goes up. As the confidence level goes down, the margin of error goes down. So we want the smallest confidence level. Well, our smallest confidence level is 90%. So that gets rid of these. So we're looking at A and D. Now, here's where things are tricky. Remember, our formula is P hat plus or minus Z star, P hat, Q hat, and N. As P hat approaches 0.5, as P hat gets close to 0.5, we have our largest standard deviation. So P hat close to 0.5, largest margin of error. So the one that in 0.23 is closer to 0.5 than 0.15. So this one will give me my smallest. All right, the farther I am away from 0.5, the smaller I get. Here's how I check it. 0.15 times 0.85. Or we have 0.23 times 0.77. Let's take the 0.15 times the 0.85. 0.15 times the 0.85. That's 0.1275. That's a smaller, that's a numerator. Or we have 0.23 times 0.77. And this one is a larger. The larger the numerator, because it's multiplying, the wider it is. So this is smaller, that's smaller. So consequently, A is my smallest. All right, number 42. Which of the following statements is incorrect? The significance of level of a test is the probability of a type 2. That's false. The significance level of the test is alpha, and alpha is the probability of a type 1. This said type 2. This is incorrect. Our answer is A. All right, number 43. Before televised debates, a poll of 800 registered voters showed 560 in favor of a particular candidate. After the debates, a poll of 600 showed 450 in favor of the candidate. Is there sufficient evidence that the popularity has increased? All right, so we have basically this. HO, P1 equals P2. HA, the popularity is, the second poll is greater than the first poll. And basically I'm saying P1 is my first poll, P2 is my second poll, saying the popularity, is it greater? Well, basically, remember, we're going to have to do, we have an interesting formula for this. It's basically going to be P hat 1 minus P hat 2 over P combined, Q combined, N1 plus P combined, Q combined, N2. So we know we're going to have denominators of 800 and we have denominators 600. All right, so this is going to be 800 plus 600. And we need to calculate P hat C and P hat Q. Well, remember, P hat C equals X1 plus X2 over N1 plus N2. X1 is 560 plus, I'm running out of room. I need to grab a sheet of paper. Then I'll just scoot it over here. 560 plus 450 over the 800 plus the 600. So let's check that out. 560 plus 450. So 1010. And then this is 1400. So divide that by 1400, and we end up getting 0.72. So 0.72 times 1 minus that. By distributive property, this goes in this numerator, this goes in that numerator. Letter B is my answer. All right. Once again, this equaled 0.7214. All right. And so that's P hat C. So P hat C goes here. 1 minus that gives me Q hat C. And by distributive property, this goes in this numerator and this goes into that numerator. There, you get to tell your math teacher use distributive property.
Okay.
Please remember, we only use this formula for two sample proportions. We only use P hat C for two sample proportions. We only pool, which is what this is, when we're doing two sample proportions. And we do not pool and we only do it when we're doing a hypothesis test. We do not do it for confidence intervals. We only do this for hypothesis tests for two sample proportions. We do not do this for confidence intervals. Number 44, a researcher has conducted a survey using a simple random sample of 50 registered voters to create a confidence interval to estimate the proportion of registered voters favoring the election of a certain candidate for mayor. Assume that a sample proportion does not change. Which of the following best describes the anticipated effect on the width of the interval if the researcher were to randomly survey a sample of 200 rather than 50? So this is where we're going to use Mr. Spencer's little formula, all right? Which is, what's the impact on a sample size? 1 over the square root of the new one over the original. All right? Well, our original one was 50. Our new one is 200. Well, 50 goes into 204. So I have 1 over the square root of 4, because 50 goes into there. The square root of 4 is 2. So 1/2. All right. So the new interval will be 1/2 the original interval. The new interval would be 1/2 of the original interval. Number 45, suppose P equals the proportion is 0.6 and the true population proportion is 0.6. The alternative is greatest proportion is 0.6. And the power is 0.8. Which of the following is true? So which of the following is true? If power, okay, power is the probability of correctly rejecting the null. So if you're supposed to reject, if the null is false, if this is false and this is true, and our power is 0.8, the probability of correctly rejecting is 0.8. But also remember, power equals 1 minus beta. So 0.8 equals 1 minus b. So beta equals 0.2. And beta is the probability of failing to reject, all right, if the null is true. So if 0.7 if it's really true, if this is the alternative. In other words, if this is false and if this is true, the probability of failing to reject is 0.2 because power is 1 minus beta. All right? So the probability of committing a type 2 error, the probability of committing a type 2 error is 0.2 because our power is 0.8. So if this is true, the probability of a type 2 error is 0.2 or 1 minus the power. All right. Using the same data, one student performs a test with a null p equals 0.85, an alternative not equal to. So basically, he ran a 2-sample test. So this is two-tailed, so this is a two-tail. And the second one runs a one-tail, both use an alpha of 0.05. All right. The first student claims there's not enough evidence. So the two-tail says not enough. But the one-tail says there is enough. Which of the following could be the test statistic? So let's set this up. Well, the one-tail did a one-tail lower tail. So alpha is 0.05. So let's calculate a z statistic. Let's calculate a z value right here. So we're going to do a second VAR's inverse norm. Second VAR's inverse norm and 0.05, mean of 0, standard deviation 1, and I get a value of negative 1.645. If he gets a z-score, less than negative 1.645, he's rejecting. So anywhere from negative 1.645 to negative infinity, he's rejecting. That gets rid of this one, and this one. That's less than negative 1.645. This is less than negative 1.645. So now let's look at the two-tail. By the way, this was the one-tail. The two-tail, alpha equals 0.05 for both of these, but the area in this tail is 0.025, and the area in this tail is 0.025. Well, we know we only need to look at the lower half because this one rejected, and so they couldn't reject with any of these. So he rejected, but this one didn't. So I need to get the z-score associated with 0.025. So second VAR's inverse norm, 0.025, and I get negative 1.96. So this guy would reject with any value less than negative 1.96. He would definitely have rejected with this one because that's less than negative 1.96, but he would not reject it with a negative 1.8. However, this negative 1.8 is in this rejection zone, but it's not in this one. So the first one does not reject with a negative 1.8, but this one does. Pretty important concept right there. All right, number 47, a political action group wishes to learn the government approval rating on the environment. From a past study, they know that they will have a poll of 270 people for the desired level of confidence. If they want to keep the same confidence interval and have a margin of error 1/3 the size, how many people will they have to poll? So this is going to be back to 1 over the square root of new over the original. All right. So they'll have a poll of 270. All right. So I need this so this needs to equal 1 over 3. So basically, when I take the square root of this, this is going to have to be 3 times larger. Or I need to end up with a 3. When I'm done with this part right here is going to need to equal 3. So basically, the 1 is 1, so I don't need to worry about this. I need to do this. The square root of n over 270 needs to equal 3. If I square this whole thing, that gives me n over 270 equals 9. So 270 times 9, $2,430. I would need a sample size of 2,430. And if it'll make you feel better, let's go back and check. 2430 divided by 270 equals square root of that. So that'd be 1 over 3, which is the 1/3. All right. So that one is 2,430. All I did was sit there and go, you know what? I can ignore the numerators because they're the same. I only need to look at the denominator portion and say, and square it, take that off, and n over 270 equals 9. All right, 48, there is a question on. I'm going to make that the very last one I do just because it's a confusing problem and not something that you're going to be required to know. Just plain not going to be required to know for this test. It has showed up on an AP exam, but it will not show up on one of your tests. All right, number 49. Men and women were, so I'll come back to 48 in a moment. Men and women were surveyed as to the ideal number of children a family should have. For 500 men, the mean was 2.95 with a standard deviation of this. For 458 women, the mean was this, standard deviation of that. Assuming all assumptions are met, establish a 90% confidence interval for the difference in population means. All right? So, first off, what's our formula? We're working with means. So that's going to be X bar, and then what did we have first? They did the min first. X bar M minus X bar women plus or minus T star. And I guess I should have written the formula down. S over the square root of N S1 squared over N1 plus S2 squared over N2. So we know it's not going to be this one. We know this is wrong because we're going to need 1.65 squared over excuse me, it was 1.65 over 500 plus 1.8 squared over, what is it? Where's my number? 450. So let's look for that. So that's my best answer right there. We're actually already done because that's the only one that has the values I needed. Wow, I thought I was going to have to do more work than that, but I didn't. I don't know who asked for 50, but thank you. This is one we should definitely talk about. USA Today reported that the speed skater Bonnie Blair had won the U.S. Heart according to a USA Today CNN Gallup poll conducted on the final Thursday of the 1994 Winter Olympics. When asked who was the hero of the Olympics, 65% of the respondents chose Blair, who won 5 gold medals. The poll of 615 adults done by telephone had a margin of error of plus or minus 4%. What of the following best describes what is meant by the margin of error? Please remember, p hat plus or minus z star, p hat q hat over n. This is my margin of error. So essentially we're saying, in this case, 0.65 plus or minus 0.04. So between 0.61 and 6.69% of the population, the true population proportion that likes this person or thought that they were the best, the sweetheart, lies within this interval. So the difference between the sample percentage, which is 0.5, and the population proportion is less than 4%. We do not think, we believe that it's not going to be lower than this or higher than this. So it differs from this by no more than 0.04. So our answer is E. All right, now I skipped number 48. Changing from a 95% confidence interval estimate for the population proportion to a 99%. With all of the things being equal, how much does it change? So let's do a norm CDF for 95%, or an inverse norm. So second var is inverse norm, parenthesis 1 minus 0.95, close parenthesis, divided by 2, mean of 0, standard deviation of 1. And I'm going to end up getting negative 1.96. All right. So in my denominator of what I'm going to do, I'm going to want a norm CDF for the 95%, which is going to be from a negative 1.96 to a positive 1.96. That's going to be my denominator. I'm going to need to do the same thing for my numerator, but I'm going to do a norm CDF. This was the 0.95. This is a 99%. So let's get the 99% values. Second var's inverse norm, parenthesis 1 minus 0.99, close parenthesis, divided by 2. And I end up getting 2.57. So from negative 2.57 to positive 2.57. Now, please think about this real quickly. First off, if we go from, as our confidence level goes up, our interval or margin of error goes up. So going from 95 to 99 means it's going to go up. So we're going to increase. That gets rid of our decreases. And the good news about this is as soon as we get rid of those, we're down to at least 3 choices, A, C, and E. It turns out we can actually do this. So second var's normal CDF lower bound. Where did I put my paper? Negative 1.96 to 1.96. So that's for the 95%. So negative 1.96 to upper bound 1.96. Oh, I'm sorry. So this distance here, hold on for just a moment. Let me pause. Sorry about that. So my range from negative 2.57 to 2.57 means my numerator is 5.14 across. So this distance from here to here is 5.14. All you have to do is say 2.57 minus a negative 2.57 tells me from here to here on the number line is 5.14 across. In the denominator, we have 1.96. We are 3.92. from net. So 1.96 minus a negative 1.96 is 3.92. So in this case, 5.14 divided by 3.92 equals 1.31. So there's a 131% increase. So basically our interval increased by 31%. Why? There's more data in the center than there is in the tails. So consequently, it gets more spread out. So the interval width increased by 31%, even though we only increased the data by from 95 to 91.9%. Once again, I would not stress about problem number 48.